All right, in this video, we're going to go over how do we graph a rational function. Okay, so I think the best way to get this thing started is let's jump into an example here. So for example, let's say we have the function f of x equals x cubed over x squared minus 4. First thing I want to do before you do anything, a general rule of thumb is if you can factor it, go ahead and factor. So I notice my denominator is a difference of squares. So what I want to do is, I'm sure y'all can see that. What I want to do here is I want to come in here and I have x cubed over, and I want to factor that difference of squares, and it factors into x minus 2 times x plus 2. Right, hopefully you can see. Let me rewrite that. Okay, so there's our factored version. Here we go. Now that we have it factored, let's talk about the domain. Okay, so the domain of any fraction is going to be, all real numbers except for those that create zeros in our denominator. Why is that? Because if we divide by 0 in the denominator, that creates an undefined function. So what do? We take both of our factors, set those equal to 0, and we say that our domain will be all reals except when x is equal to both a positive and negative 2. Once again, how do we get those? You just take both those factors, set them equal to 0. All right, the next two bits of analysis, holes and vertical asymptotes. These two are related to each other. So a hole is literally a hole in a graph. I mean, if you look at the graph, there's literally a hole in the graph. But how do we figure it out from looking at our function? A hole occurs whenever a factor cancels. And so as we look at our graph, look at our function here, nothing cancels. Therefore, we do not have any holes. I'm gonna put in no holes. And because we have two exceptions, and both a hole and a VA have to come from the exceptions, these are not part of your graphs, they're not part of your domains. So that means if I have two exceptions, if none of them are holes, then that means that I have by default two VAs, and they have to be x equals both your positive and negative 2. Okay. Little key, if you're doing your homework, remember when they say what's the equation of the vertical asymptote, make sure you write in x equals negative 2, x equals positive 2. If you put just the numbers, you will get it marked wrong. All right, let's talk about horizontal asymptotes. So horizontal asymptotes are based off of the degree, which is the highest power, of both your numerator and denominator. In our case, in our function, our degree, look at the original function here, the degree in the numerator is 3, the degree in the denominator is 2. So since the degree is larger up top, we have no horizontal asymptote. Okay. Next, let's talk about an oblique asymptote. Okay, just another type of asymptote. And what are asymptotes? Just asymptotes in general. Whenever you graph your function, your graph is going to hug. It's going to get super close to these asymptotes. So that's all it is. So these asymptotes kind of give us guidelines as to how the graph should look. All right, so oblique asymptote. An oblique asymptote is a special asymptote where it occurs in the very special case whenever the degree of your numerator is exactly one more than the degree of your denominator. And that's exactly what we have going on in our instance here, because our degree up top is 3, degree at the bottom is 2. So how do you figure out the equation of your oblique asymptote? Well, you need to, unfortunately, do some long division, some polynomial long division. Okay, so I'm going to take, in my house, I'm going to put the x cubed, and I'm going to put my missing terms in here, 0x squared plus 0x plus 0, just because it makes it easier for my terms to line up. And then that's going to be divided by x squared minus 4, once again adding in my 0 term there. And what do we do here? We ask ourselves, okay, what do I multiply x squared by to get it to become a 1x cubed? That's a 1x, so we're going to put that there. All right. We then multiply the x by the x squared minus 4. So x times x squared, that's an x cubed. X times a 0x, that's a 0x squared, which is really nothing. And then x times a negative 4 is a negative 4x. Okay, just like long division, I want to subtract these. And I'm left with x cubed minus x cubed is 0. 0x squared minus 0x squared is 0. 0x minus a negative 4x is a positive 4x. And when it comes to oblique asymptotes, you do not care about the remainder. So the oblique asymptote has the equation y equals x. So once again, oblique asymptotes only occur when the degree of the numerator is one more than the degree of the denominator. If that's not the case, you will not have an OA, no oblique asymptote. All right, here we go. Just a little bit more, then we'll graph. What we want? X-intercept. Why not? Seems like we've been doing this since the beginning of the semester. X-intercept, you know the drill. You take your function, x cubed over x squared minus 4. We set that equal to 0. I want to solve this for x, so I want to get rid of my denominator. So that means I multiply both sides of the equation by our denominator. Okay. The left side cancels, and I'm left with just x cubed on the left side. And this equals, well, 0 times x squared minus 4 is 0. All right, we need to take some cube roots. And because it's an odd root, because the index is 3 there, we don't have to worry about pluses or minuses. So x is equal to 0. So the x-intercept, if I wanted to write in ordered pair form, is 0, 0. Which, without doing any work, that means automatically that my y-intercept is going to be the exact same thing. Why is that? That's because the origin is the only point that touches both your x and y axis. If you don't like that explanation, you can go through the process. The process is this. Let's do this. Y equals, I'm just going to rewrite our function here, f of x, which is y. It's x cubed over x squared minus 4. And for your y-intercept, you set all of your x values to 0. All right, 0 cubed over 0 squared minus 4. You get 0 over negative 4, which is legal, which gives us 0. So the y-intercept is the point 0, 0. So as I told you, the x and y-intercept are both 0, 0. All right. So now, I think we're ready to graph. Let's do so. Here we go. Let's get our axes going. Whoa, this little crooked. Don't judge. All right, the first thing I like to do is I like to plot my vertical and horizontal and oblique asymptotes. And I'm sorry, you're never going to have both horizontal and oblique asymptotes. You're going to either have one of each, if at all. But let's talk about vertical asymptotes. Vertical asymptotes, you're going to have them at plus and minus 2. So let's do that here. So here is, I'm going to indicate them with the dotted line here. So the green dotted vertical line here is our vertical asymptote. That's positive 2. We also have one at negative 2. Let's do our oblique asymptote, which is y equals x. So that's just your your line on y equals x, which has a slope of 1, y-intercept of 0. So what I'll do is I'll put a point here, right? So the y-intercept is 0, 0. And then we have a slope of 1, so up 1, right 1, or we can go down 1, left 1. Either way you want to do it. The slope should be 1 either way. And y'all get the point. A little crooked, but it's kind of hard to draw on a tablet. All right, so that is our oblique asymptote. And so the key thing when looking at graphs of rational functions is that the vertical asymptotes really break up your graph into these distinct or different parts. We can never, ever, ever, ever cross a vertical asymptote. Okay, sometimes you can cross a horizontal asymptote, but we'll save that for another lecture. But think of your vertical asymptote as breaking this up into 3 parts. I'm going to have a part of my graph that's to the left of the leftmost asymptote. I don't know if you can see my mouse here. There's going to be something on this left side here. Okay, I'm going to have something in the middle in between the 2 asymptotes. And then we'll have something to the right. Okay? So how do I know what goes where? Well, let's get some ordered pairs. Let's get some points here. Okay? I'm sorry, let's plot our x and y intercept, which is already plotted. Okay, 0, 0. All right, but let's get some ordered pairs here so we can get a feel for this graph here. And the way I'm gonna do this is I'm gonna go to my calculator. All right, let me get out of this. Let me double check I'm in the correct settings. My independent is on as, that's what I want. So here we go, y equals, our function was x cubed divided by the quantity x squared minus 4. Okay, I want to go to my table. And what I want to do, I'm going to delete these out here. What I want to do is I want to grab some values that are outside of these vertical asymptotes. So let's say -2 is our leftmost vertical asymptote. So let's look at -3. When x is -3, we get a -5.4. In fact, to prove to you that vertical asymptotes are not part of our domain, check this out. If I type in a -2, I'm going to get an error because it's a vertical asymptote. That's where our function becomes undefined. Anyways, -3 gives us a y value of 5.4. -5.4. Was it negative? I don't know. Yeah, it's negative. Okay. And so that point should be, let's see, that's -2, -3, -1, 2, 3, 4, 5.4, somewhere here. Okay. So what does it mean when a point is there? Well, like I said, think of these asymptotes as kind of like guidelines or guiding your function as to what it has to do. So what that means is that if my point is here, it means I am trapped in this triangular pie-shaped region, okay? Because I got to get close and I have to hug these asymptotes. That's what asymptotes mean. So that means that as I come to the right here, let's get a different color. As I come to the right here, I want to get close to that vertical asymptote and I'm going to go down. Why do I go down as opposed to going up? Well, if I go up, I'm going to be bumping up against my oblique asymptote. And I want to avoid that. I want the path of least resistance. Think of it like that. In a similar fashion, as this kind of hooks over here to the right, it's going to do the same thing. It's going to hug that oblique asymptote there. Okay? So that's our left region here. Let's talk about the middle region. For the middle region, I like to get a couple points here. So let's do -1, +1. And let's see what those values are. Okay, so we get a +1/3 and a -1/3. So a +1/3 and a -1/3. All right, so -1, +0.33, that's somewhere here. Okay, +1, -0.33 is somewhere here. Now, what does this mean? As I go to the left here, taking that, it's got to go that way because I want to avoid bumping into my oblique asymptote there. And I want to hug that vertical asymptote there. I got to connect to my x and y intercept. And then we're going to come down here and we're going to hug that vertical asymptote there. Okay, so this time we were able to cross through that oblique asymptote there. Okay, but the key is you got to hug those vertical asymptotes. All right, and then one more. We got the right side. Let's once again grab an x value of this time a +3. Let's see what that gives us. It's a +5.4. So that point will be 1, 2, 3, 4, 5.4, somewhere here. And once again, hopefully you're seeing the pattern. Now we're stuck in now this pie-shaped region here. And as before, it's got to do something like this. It has no other option but to do something like that where we're getting super close to those asymptotes. Okay? That's how you graph these rational functions. It's very important. Just go through, look for your vertical asymptotes, your horizontal asymptotes, your oblique asymptotes, and then just kind of grab a few points and see what happens. All right, really quickly, I want to go over this example. Do I have another one? Yeah. So this one's already graphed for us, and so I just want us to quickly go through and analyze it. Okay, so really quickly, we know that if we factor that denominator here for this example is the difference of squares again. And once again, it's x minus 2 times x plus 2. All right, let's come over here and do a quick analysis. So our domain will be all reals except what? Yeah, positive, negative 2. Will we have any holes? No. Nothing's canceling. That means we're going to have two vertical asymptotes at both a positive and negative 2. So we should have two vertical asymptotes. Okay. Horizontal asymptote. Well, let's see here. The degree of the numerator is 0 because there's not an x there. The degree of the denominator is 2. So that means that our degree is larger on the bottom. In this case, we will have a horizontal asymptote. And it's going to be the equation y equals 0. That's what happens when your degree is larger in your denominator. Okay? And because we have a horizontal asymptote, that means we will definitely not have an oblique asymptote. Okay? Because you can't have both an HA and an OE. All right? X-intercept, I don't think we're going to have one. So how do I know we're not going to have one? That's because if I take our function 3 over x squared minus 4, if I set that equal to 0, and if I try to solve that, so let me multiply both sides by x squared minus 4. The left side cancels, we're left with just 3 equals, well 0 times x squared minus 4 is 0. This doesn't have a solution. So maybe I should put an x there. Let's say no solution. So that means there's no x-intercepts for this graph. This graph is not going to touch the x-axis. All right. And lastly, let's talk about the y-intercept. That means just plug in 0 for x. That's going to be 3 over 0 squared minus 4. That's going to be 3 over negative 4, aka a negative 3/4. So our y-intercept is going to be at 0, negative 3/4. Okay? All right, so how can we use all this information to see where they got this graph from? Well, first of all, what's important I didn't tell you here is that the tick marks are going in increments of 2. So this is 2, 4, 6, 8, so on and so forth. So right away, we can see our vertical asymptote at, coming right down there, x equals positive 2, x equals negative 2. Oh my goodness, my pen's all over the place. But you guys get the point, right? You see how the graph is hugging those vertical asymptotes. Our horizontal asymptote is y equals 0. Notice you see the graph getting super, super close. As x goes to negative infinity, as x goes to positive infinity, you see it's getting really, really close to those horizontal asymptotes. We see our y-intercept at 0, negative 3/4. And what we notice is if we were to go in, I won't do it, but if we were to go in, and let's say we wanted to figure out, actually I'll write it right here in a different color. Let's say we wanted to grab some points really quickly. X f of x. Okay, let's say when x is let's do negative 3. When x is a negative 3, what would that mean that y would equal? Just plug that into your function. So 3 over 3 squared minus 4. So let's actually do this by hand. So 3 over 9 minus 4. So I went ahead and squared the negative 3, positive 9 over 4. Okay, so that's a positive 3/5. So negative 3, positive 3/5 is this point right here. Now see that? And what do we talk about? As we go to the right, we're going to hug that vertical asymptote. As we go to the left, we're going to hug our horizontal asymptote. Okay? How do they get the shape in the middle here? Okay, well, let's grab a couple points. What about when x is a negative 1, when x is a positive 1? Well, when x is a negative 1, we're going to get 3 over 1 squared, negative 1 squared, which is a positive 1, minus 4. So that's 3 over a negative 3. That's a negative 1. So we have the ordered pair negative 1, negative 1, right there. Okay, when x is a positive 1, we're going to get the exact same thing. And that's where that point comes from. Now see that? Combine that with our y-intercept that we've already graphed, and you can see that it has no choice but to do what it does to the following. It goes to the left, it's going to get close to the vertical asymptote. Goes to the right, it gets close to the vertical asymptote. And then if I were to pick a positive 3 as our last graph, or as our last point, it'll be 3 over 9 minus 4, which is a positive 3/5, and that's the point right there. Okay, so in your homework, just be prepared to understand how they got the graphs that they got. All right, see you guys in the next video.